Our next speaker is Kanav Gupta. He is a PhD student at the University of Maryland and kind of continuing within our theme, but this time we're going to be focusing on addressing issues with latency and efficiency within this domain.
Okay, I'm going to present Sigma. This is a framework for secure GPT inference using function secret sharing. And this is a joint work with Neha, Ananta, Nishant, Divya, Ashish, and Rahul. As we all know, LLMs are everywhere. These days, LLM have been deployed as a service by these large companies like Microsoft and Google. And clients can just query these models as a service to deploy it on their servers by just sending their query to these parties and getting their response back. Unfortunately, this raises a serious privacy concern, as the client has to reveal their input query in clear to these services. In an ideal system, we require that the client doesn't learn anything about the model of these proprietary companies, and the companies should not learn anything about the input of the clients. This is a problem of secure transformer inference, and while it can be solved using generic 2PC techniques, the overheads of standard 2PC like Gabor circuits are prohibitive. So in this work, we consider the model of 2PC with pre-processing. That is, in a pre-processing phase, a dealer provides the correlated randomness to the two parties, and in the online phase, these parties can then plug in this correlated randomness and their respective inputs to learn the final inference output. In this work, we focus on reducing the cost of the input-dependent online phase. This is also a very popular model, and previous works of Krypton and Piranha have adopted this model to accelerate their online phases. Before moving into the technical details, I'll quickly go through our results. We are able to achieve a single inference of GPT-2 in just 1.5 seconds, and a huge Llama 2 13 billion model in just 38 seconds. This is 19 times faster and communicates 10 times less than the previous work of Krypton. We are the first ones to scale to as big as 13 billion parameter models. We provide efficient but precise approximations of the complex nonlinearities that occur in transformer models. And our framework does not require you to retrain your underlying model to be plugged into our system. Okay, let me briefly discuss the architecture of transformer model. Like any other machine learning model, there are two kinds of functionalities occurring inside the model. We have linear layers, that is nothing but matrix multiplication, and that can be done very efficiently using Beaver multiplication in the preprocessing model. However, like always, nonlinear layers are the key bottleneck in transformer inference. This is because of two reasons. First, that we require secure computation of complex functions like inverse, like negative exponential and inverse. And the second reason is that we have to call these underlying functionalities many times, like millions of times. So in particular, transformers contains three kinds of nonlinearities. First, we have GELU, we have softmax, and layer norm. So to understand the cost of these nonlinearities, we run GPT Neo on Krypton, and we see that just calculating all the ReLUs, we require 20 seconds, which is we are calculating 25 million ReLUs. In all our prior works, this large cost is mainly due to the communication that is required in these protocols. So to overcome this issue of communication, too much communication, we use function secret sharing based 2PC. Without going into details about how FSS works, I can explain to you the three properties of FSS based 2PC. First, it has very low communication complexity compared to Gabor circuits or secret sharing based works. It has a low round complexity, but we have a higher compute compared to secret sharing based protocols. But we think that this is not a big problem. Why? Because a previous work of Orca showed that these protocols can be very efficiently accelerated on GPUs, and hence the problem of higher compute becomes not so big. There are a few building blocks that are already known using because of FSS. That is, we can compare two n-bit integers. We can calculate the arithmetic right shift of an element, and we can also do n-bit LUTs. Although this we can only use small LUTs like 256 elements because the computational cost is exponential in the input size. In this work, we provide FSS-friendly approximation to these to complex nonlinearities, not just these simple nonlinearities that occur in LLMs. In this talk, I'll explain how we approximate GELU and would refer to the paper for other functionalities. Okay, let's talk about GELU. This is how the definition of GELU looks like. It's a very complex formula for GELU. However, when we plot GELU on a graph, we notice that this looks very similar to ReLU, right? Where ReLU is a very common activation function, and ReLU of x is equal to x when x is greater than 0 and 0 otherwise. So, since these are very similar, the natural thing to do is take a difference of these two things, and we call that function delta. So if we now have a protocol for ReLU and a protocol for delta, we can easily calculate GELU. ReLU can be very easily calculated using just a single call to comparison, and as has been shown in previous works. But the only challenge here is we have to calculate delta. How do we calculate delta? We use lookup tables for that. As has been motivated in the previous talks, lookup tables are a very powerful tool to compute these complex nonlinearities. However, we cannot directly use a lookup table protocol over delta because these can be over the large domain. So we make three observations before using a lookup table to reduce the domain. The first observation is that delta x is 0 outside the range -4 to 4. So this means we can significantly reduce the domain that we want to compute to just -4 to 4. Second, we observe that delta x is an even function, so we can further reduce the domain size by half, as we can only compute using the absolute value of the input. And the third observation that we make is an empirical observation that we don't need a very large precision of the input. We can just do with a small precision of 6 bits, and we can then directly plug the output to the LUT to accurately approximate GELU. After all these steps, we result in a number that lies between 0 and 256, and hence can be calculated using an 8-bit lookup table. All of these underlying functionality that we see, clip, absolute, and truncate, all of these can be efficiently implemented using the existing protocols. But what we do in our work is that we further shuffle these protocols, keeping in mind the costs that occur due to FSS, by reducing the comparison size and number of comparisons. I would refer you to the paper to understand the remaining optimizations that I'm missing out in this slide. So now let's move on to the evaluation of this work. The first is about accuracy. We notice that for all the tasks that all the popular tasks that we see in transformers, our accuracy matches the accuracy of the corresponding PyTorch evaluation, and this also comes with the fact that we do not need to change any of the underlying model. We can directly use pre-trained floating point weights and plug it directly into our system. Then let's move on to performance. Even in all kinds of models, the smallest models to medium-sized models and large models like Llama 13 billion models, we see a significant speed up compared to the baseline of Krypton. We see a speed up of 19x for a tiny model like Bird Tiny, and 12 to 13x improvement for medium-sized models. On the other hand, Krypton fails to scale to extremely large models like Llama 13 billion or 7 billion models, while our system gracefully extends to these larger models. With that, I would like to conclude my talk. And in conclusion, we are the first system that computes the transformer inference of multi-billion models, and we provide approximations for FSS-friendly approximations for complex nonlinearities like GELU, softmax, and layer norm. And while these are efficient, these also preserve the accuracy of the system. The code is available online, and I'm happy to take any questions.
Thank you very much for the talk. I'm Son from Arizona State University, and I have an impression first. It seems that you, when you compress the size of the input, the model, to like 6 bits or 8 bits, if I understand correctly, then the result is not decreasing so much. And I think it's somewhat similar to the phenomenon that people found online, that when they compress the model into just like 3 values, -1, 0, and 1, the model performance doesn't decrease very much. So I wonder if you have done any experiment on what is the optimal value of the bit that you can compress?
So I'm aware of the work that you're talking about, the ternary bit LLM works. However, we found out that there are some additional function blocks that make them not very crypto friendly. So we haven't explored them to the fullest till now. Thank you.
Thank you for your talk. So you mentioned somewhere in your presentation that FSS, they are computationally expensive, right?
Mm-hmm.
So do you have made the comparison with some other MPC techniques, or is it you just assume this thing?
I don't have a number, but we have done experiments, and the last time I ran the experiment, if I remember correctly, it was like 2 to 3 times expensive.
From the previous MPC techniques, like Garble circuit and
Yes.
secret sharing?
Yeah.
Okay. And you have used the 2PC, the FSS only for the nonlinear activation functions, right?
Sorry?
So you have used FSS only for the nonlinear
Correct.
activation. Okay.